Good afternoon, everyone. Thank you for joining. Today's session will be on Marc and Mentat. To be honest, I will spend more time in Mentat than Marc specifically. There's a couple of, let's call it quality of life, lack of a better term, features in Mentat that not a lot of people are aware of or use that efficiently. There's also a couple of tools we know about and we don't use it a lot. So I'll spend a bit of time on looking at some of these features available in Mentat. So let's start with, if there's a contact analysis, one of the first things I look at is the contact status. So what is the contact status? Okay, so contact status is usually a value from 0 to 1. 0 means it's not in contact, 1 it is in contact. But that's not the whole story. In Nastran, as far as I'm aware, it's still 0 and 1. Marc has got a couple of additional values. So if we look at that, that section has got a 2, and these look different as well. So let's start by switching off the contact body so we can see better what's happening on the inside. If I rotate this, we'll see I've got at least 3 different values apart from 0, which is not in contact. So let's have a look at those. And tip, here's a feature that makes it a bit easier. So I can say add a couple of points. And I want to see what the values of these locations are. Let's add I know it should be 0, but let's add 1 there. So there you can see a value of 1 as expected. So that should be touching. I've got a value of 1.5. I've got a 0.5 and I've got a 2. So what does all of these separate values mean and when do we see them? So the first one, the value of 1 is as expected. That's for touching contact. So these nodes, effectively all of them are in touching contact. The value of 1.5 means it's in glued contact. You'd almost expect 0.5 to be almost in contact, and that's actually what it means. For thermal analysis specifically, if there's a small gap between 2 parts, heat can already be transferred between them through convection and radiation and so on. And the equation and the method to do that is a lot simpler than trying to do radiation for a complex structure. So for this, 0.5 means it's close to in contact, but it's not yet in contact. So heat transfer takes place. Value of 2 is used for cyclic symmetry. So cyclic symmetry, let's just switch this on and rotate so you can see a bit better. So if I switch it off my results, I go back to my model. To do cyclic symmetry means I take that and I copy it across and I keep on copying until I get the full model. So as long as my lows are cyclic symmetry and my structure is, it's a very efficient way to model and to look at results. So what you see there, if I look at it straight on, you can see these 2 angles, those 2 curves are 15 degrees apart. And to activate that, I just need to go to my job. You'll just notice I've got a node to segment and segment to segment job. Both actually work and give almost exactly the same answer. For cyclic symmetry, I activate cyclic symmetry. I need to specify a point. Now that is any point on that center axis and a direction for that axis, which is in the global X direction. And that's almost it. The second thing I need to specify is simply how many of these are copied to form the full circle. So if I change that argument, say to 12, you'll see it calculates a 30-degree angle between them. Now there should be 24, so I don't want to change that. You do not need to specify contact bodies for this to work. It'll automatically take all elements, copy it across, and check if that side touches this side. Okay, so the advantage of this is we don't need the same mesh on the left and right side for this to work. The Nastran original algorithms require that the left and right, there should be a 1-to-1 node relationship. So the cyclic symmetry in Marc uses the contact algorithm, which is why we see a contact status. The second one is if I switch between touching and glue, if I look at my contact table, I've got touching contact between that center part. Let's just add the names, you can see which is which. So body 1 can touch body 2. For node to segment, I simply wanted my contacts from there to there, there to there, and there to there. Otherwise, these would have been filled in as well. So that's touching, glued, and touching again. Now the difference between these two is simply the initial contact state. So if I look at both of those, they actually use the same interaction. If I go to interaction, and this is specific for a thermal structural analysis. So for the structural part, I've set up my defaults, and then I can change to the thermal side where we can specify thermal conduction coefficient, in other words, a touching contact heat transfer coefficient, and then we specify a near contact distance. So if these are within 0.02 of each other, this whatever units you're working in, then they'll start to transmit heat. And to specify exactly how much, you go through this where you can specify heat transfer coefficients, distance dependence on that, natural convection, radiation, and so on. Okay, so I just used a small value just to show you the difference there. So this value is set to 50 for the near contact heat transfer coefficient. This one is set to 100, which is double that. And then for the glued contact, what we also have is an option that says, how is the heat transferred? Is it a perfectly conducting phase? In other words, it's actually one material. I just broken it into separate glued parts because I want to use a different mesh size, a different element type, or is it actually two parts that should be glued together? So if I want a glue with certain properties, I can change this to switch up the constant temperature at that interface. I can specify a heat transfer coefficient. So if you activate that, which is the default, at least in the latest version, it's perfect heat transfer at that location. Okay, so if I now go back to the model again of the results and plot in this case the temperature first, and activate temperature. So everything starts at 20. I apply a high temperature, I think 100 there and 50 on the outside. So you can see how the temperature is transferred between the different regions. So what you should see is that the three parts does not have reached the same final temperature. This is because this is glued, perfect heat transfer. On this side, it's in contact, but it's not perfect. So I specified the contact heat transfer coefficient, and there the same contact heat transfer coefficient was used, but it's not in contact, which means it used the near contact values. Now, by the way, there is one additional result. You have to ask for it. There's a near contact distance as well. So in this case, it will tell me what that distance is. So these started with a gap of 0.01, and as it heated up on the inside, that actually closed down a little bit. Now, something that's not that obvious from this is if I look at the contact status, you'll notice that there's something kind of wrong on those nodes. So it doesn't look like it's making contact. So if I change this thing to not show the one on that side, let's hide the last one, and I now plot again that same near contact distance, you'll see that these have actually opened up. So there's still heat transfer across to those nodes that is now based on a much smaller, so this is an order of multiple orders of magnitude smaller than that tolerance there, which is why we didn't see that if this one was active. Okay, so that's just a bit more on contact state. So if I just plot the contact status and numbers again, you can see then a value of 2 is that cyclic symmetry. A value of 1 on that interface is for touching contact. 1.5, which is that orange color there, is for glued contact. And then the last one is near contact, which is this kind of a blue color. Good. So next thing I want to talk about is the a bit more, let's spend a bit of time on this form over there, which is something I find extremely useful, but not a lot of people use it or use it efficiently. So this tool helps you to select stuff, and if I create a boundary condition, I can then whatever is selected there add to a boundary condition. So let's start with something simple. I'll create a boundary condition on this, which I want to constrain 𝗪𝗁𝗁𝗁 in these directions, and I'm just going to move it out of the way temporarily. So the single method is if I use nodes, these are now added, and if I add it to this, I can add that list. That is kind of pointless. I can do the same there as there. This becomes more useful once I start using something like path. If I say nodes along a path, I can say from there to there, up to there. Okay, and then it selects it along that line. Now, the reason I selected these internal ones is it's trying to find the shortest distance, but shortest distance from there to there, argument's sake, there's more than one. If I do that, you'll see some kind of a random pattern to get there. But it could also have gone there and there. So if you need a specific direction, you have to give it a bit more guidance in terms of how to get there. But this is really useful if I need to constrain 𝗪𝗁𝗁𝗁 and edge. So I'll say from there to there, all of those nodes. And if I say add, these buttons are the same as those. I can say all existing, which will be everything in the model, or I can say all the selected. Selected here means whatever is selected in this tool. So if I say all selected, I switch off boundary condition, just activate it again. So there I see all of those now have the boundary condition active. Okay, we also have options like box and user box. They're very close to the same, so not too important. If I specify nodes, I can specify range in X direction. So that point is at 0, 0, sorry, that one is 0, 0, 0. So let's say from in the X direction from -1 to 1, it should be somewhere over there. Then in the Y direction, let's just show the coordinate system. Y direction, I want it from 1 up to, let's say 3 to ensure that it's fully enclosed. And the Z direction, just I want everything, -1 up to 1. Okay. So just double check. Sorry, that point is one not there. So let's just try again. So -1 to 1, 0 to 1, and -1 to 1. Okay. So this is useful in a scripting environment. If I need to, let's say, mesh in Apex or something, and for whatever reason I can't already predefine loads of boundary conditions or some feature there which I'll need on this side. If I know where it is, I can then, using this kind of box selection, automatically select it. Okay, the next one, then important one, would be plane and its buddy, the phase flood. So I'll do phase flood first and then I'll get back to plane. So phase flood says, let's make this 5 degrees. And I'll use different values and we'll see what happens. If I pick that phase, I think these were 2.5 degrees angle between there and there. So I pick any phase and it fills it until it gets to a corner that's sharper than that. None of the internal phase will be selected either. If I make this 2 degrees, it should only pick one row. So let's say phases there. So because that's 2.5 degrees, it doesn't capture the rest. If I make this, let's say 100 degrees, it should be able to go around these corners as well. So let's see if that works. The reason it stops there is these meshes are disconnected. It's contact bodies is not sharing nodes there. So if I go back to 5 again, just to show what happens, it selects all of those. If I change this to a plane and I do the same faces there, Now it says from that original one, not from the one next to it, from there, if it's within 5 degrees, you're allowed to select it, which means 2.5, 2.5, but these are on the limit. So if I make that 5.5 and clear, it should be enough to select one further. Okay, it's not something we use a lot. Face plot I do use a lot, but flood not that much. Okay, oh, sorry, not the plane I don't use that much. Flood is another one that's really useful. So if I need to select all of the elements in one of these bodies and I don't yet have contact bodies, just say flood elements and I'll pick one of the nodes. And it goes through that, expand, expand, expand until all the nodes and elements attached directly or indirectly to a node is selected. We can have associations, but by default stuff is not associated to geometry in Mentat, and you can do it though. Another one would be point, curve, or surface distances. In this case, I've got a curve, so that's kind of convenient. So let's say with a distance of, let's make it 0.5 from that curve. Sorry, nodes on that curve. So then everything that's within that distance from that edge or that curve, it will select. Now another one that we can use, we can type a location would be, if I do, let's say, point distance nodes, and I specify it by distance point. Let's pick something over there, and you can see that kind of an arc-shaped, spherical shape around that point that we've selected. So again, not something I use a lot, but it is convenient, especially if I need to, let's say, you realize only too late that nodes are too far from some kind of a surface, no battle with contact. I can then select those and project it onto that surface by, as I say, selecting it based on distance. Now that's the first bit. Now this is just the basic selection stuff. After that, we have this by option. So let's use elements is the one with some of the most options. If I go there, I can say based on nodes. If I say based on that node, it'll pick all of the elements that's attached to that node. I can do the same for nodes, where I can say by element. So one example would be, let's say I have only this node, this element, but I want to grow it a little bit. I want to add more. I can say nodes by elements, pick that one. And then I can say elements by nodes. And I say by nodes, all selected. So it now selects the second row. Nodes by elements, all selected. And I keep on growing this by doing this. So this works vaguely like that expand tool that's available in Apex, or grow elements. Now that's the hard way of doing it. I was just showing you how to do this. There is actually an easier way. So let's take that element, just need to set it back to single, pick a single element, make visible. Now I want to see the elements next to it. And I'll explain why I want to do this in a later model. There's some really cool features for this. So then I can say just grow the mesh. So this works similar to the Apex one, and if I keep on doing it, at some point it will stop when it's fully selected everything in that one part. Okay, now another feature that's useful there is, so this is how we pick, but the first one is what do you want to do? So let's say I do a flood, just to make it easier. I select these and these. Those, and then I realize, but I don't want certain ones selected. So I can switch it back to single and say accept, and I pick a couple of elements and it removes that from the list. Just remember to switch that back to and, otherwise you clear the list and everything you select is not added. But similar to Boolean operations in CAD, we can do an accept, so that's an subtract. Invert, which is the opposite to what you're selecting. So if I do that, it should select the opposite to what you're selecting there. As you can see, it kind of swaps it around. Okay, and the last one then is the intersection between what you've selected and another one. So again, this is at its most useful when you have some kind of a script that automatically sets up a model. Okay, now the next one. Apologies. The next one has to do with this really confusing one of make visible. I select that and everything disappears. I say make invisible and everything appears. Now the reason for that is, let's say, again, I'll use flood, I'll say these elements. If I now say make visible, what it means is make everything invisible except this list. So say make visible, only these will be visible. If I do the same, select the same elements, and say make invisible, everything else will be made visible, even if it was invisible beforehand. So let's say I take these and I make invisible, it will then make this bit visible again. So it's everything that's not visible will be made invisible, everything that's not invisible will be made visible. Okay, so this means, and this is why, if nothing is selected and I say make invisible, what I'm saying is everything selected there, which happens to be nothing, make that invisible and make everything else visible. So that's one of those really weird things, but they try to make it consistent at least. Now, the next one is there's an option that says exclude invisible bodies. So at first glance, it says, let's say, I want to make those invisible, so they're already invisible, and then I pick these, and with that option on, you kind of expect it to exclude these, but it doesn't. What this means is if I open my contact bodies and I do that and I say make invisible, it doesn't suddenly make that one visible. So I can pick one of these and make invisible. So all of the contact bodies that's not active there will be ignored. If I switch this one off and I say make invisible, now it shows everything. Just be careful it doesn't automatically activate that one in the tree. So it's slightly confusing on that one. Okay, so that's it in terms of the selection features. It makes it easy, especially that face flood, to select something on a curved surface. So let me just select faces again. And let's say I want to select that first row of elements. So there's no option to pick elements. I can pick the faces, but I can say elements by faces. By the way, there's by class, line 2 or X8 or whatever. But I can say by faces, select, and then you see those are highlighted as well. So by doing this, it's then possible to select a layer of elements or the one closest to the face argument's sake. Okay, so the next one I want to discuss has to do with features in terms of the results that we can plot. And for that, it makes a bit more sense to look at a different one. So this is a solid mesh, simple plate with a hole in it. I want to see the stress concentration and just to show the loads and boundary conditions. So that's the constraint. And on the other side, I apply some kind of a pressure. So I'm applying a stress to that side effectively. Now, this model has one very specific and important feature. I've got a plasticity curve as well. And during the run, I plan to exceed whatever the stress is. I've set to 100 just to make it a nice round number. Yes, I know for steel it will probably be significantly higher. Okay, and with no table filled in, this means it's a perfectly plastic analysis. So my stresses are not allowed to effectively exceed 100, whatever units, MPa argument's sake. Now, if I add a curve, I could easily add one, but what I want to show you in a little bit is just going to be easier if I have something very simple that I expect. Otherwise, I need to back calculate and map onto this. So that's the only thing in this model. I then run the analysis, and let's start with plotting the von Mises stress. So it's the equivalent of stress is von Mises that's calculated from the stress tensor. And I go to the next step, and 16 MPa, 32, and so on. Now, before I go too far, this is a really irritating format. So to change that, I can go to Tools, and where's the option? In there or there. Sorry, additional settings. So there I can change it to floating, and I just want one digit after the point. I can make it 2 if I really want, but it's usually not sensible. But let's keep it at 1. Okay, so that's still in the linear range. I don't expect to see plasticity. It goes up, goes up, goes up, goes up, and it exceeds 100 MPa. Why in the world would the stress exceed my yield stress and perfectly plastic stress by 100 MPa? And the answer for that is, where are stresses calculated? And in theory then, or for the same case, the plasticity calculated. That's at the integration points, which are not at the nodes, it's somewhere inside the element. If you then extrapolate the stress there back to the node, I expect to see a higher stress. Okay, so this is, I want to see if that's the case. So then I go to extrapolation. Instead of linearly extrapolating from the integration point, I can say translate. Translate means take the integration point value closest to the node and plot it at the node. So activate this, and now the stress is at least below 100. Now this is a bit worrying. If I go to the next step, it keeps on jumping up and down, but never quite reaches 100. Now the reason for that is it has to do with averaging. So 2 elements, so that one is argument's sake 100, this one is 99. If we average, not perfectly 100. So switch off averaging, now it's exactly 100. If I go back a couple of steps, so there it hasn't deformed plastically yet. I go to the next step, and it's plastic, plastic, and plastic. Okay, so let's go to this step. It just makes it a bit easier to show some of the additional features I want to show. Okay, so as expected, the elements don't quite agree on what the stress state is. I can do the same for plastic strain as well. And I'll see different values for the different elements connected to the same location, which kind of makes sense because we're now plotting for this element somewhere over there, the plastic strain, while for this one we're plotting that one. We're just showing it on the corners. So this is why there's differences between these elements and the ones next to it. Now let's say I'm interested in a material model and I want to test my behavior. I want to see what the values on that one is. So one of the ways would be I pick, let's say, just that element and I make visible. Now I've got that one. I can, from this one, see whatever the values are on there. Now that for strain is very small, so that's why I don't see values over there. So I can change this back to, instead of floating, let's make it exponential again. Okay, so there I can see what the value is probably there. It may be there. I just know that red is somewhere in that range and blue somewhere over there. And look at the number. Remember that 5.9 is the maximum. One option I have to plot that is to say, let's plot the numbers. And suddenly the number is lower than we expect. Okay, so we'll go back to contour bands. It should be 5.9. By the way, there's useful feature there. I switch on max, and that is actually, it at least shows me where it is. But if I want to know that value, I can't use the max there. There's also a min if you're interested in it. For 𝗏𝗏, it doesn't make sense for just, let's say, principal stresses or stress in the x direction. The min also makes more sense. Okay, so how do I get the numbers at all of these nodes without having to, well, I can't use the, well, let's try the probe. Let's see what happens. Like that. And these locations. And 3.4, so this is wrong again. Now, why would it be wrong? Because the problem is, let's leave that for the moment. The problem is that this node has a value, which means for a node, it doesn't know which element it should use. So by default, it averages all the elements attached to that again, even if with this, I'm not plotting the average. So if I want to see just this element, this is what this isolate tool is about. I can say isolate this element, and now that number, that number and that one matches exactly. What isolate says is average only the elements in this list together, and then everything next to it also separately average those. So even if I show the full model, it still shows the one element that I've got, that one's values, because these nodes, because I isolated it, is associated with this one. So if I do, let's say we add another one, I can say add that one, which is not part of the isolated nodes. Add, no, isolate, sorry, wrong one. Probe this one. That node. Now that's again the average between those two. If I want to see for this element what it was, I just need to isolate that. But notice that this value will now be averaged across both of these because both of these are isolated together. Okay, so does that make sense at least so far? Okay, I assume so. Nobody's answering.
Sorry, and can you hear me?
Yes.
Yeah, sorry. Just a question that I had a little bit earlier was just a selection of internal nodes when you're doing those flood plots.
Yes.
We have a point and an offset distance. Are you selecting internal nodes as well?
It should. So it's kind of easy to check. So I'll say I think what the easiest way would be point distance from there, the distance of, let's say, sorry, there should have 0.1. Nodes. Sorry, the units of this one is different. Let me just check distances from there to there. It's 2.5. So let's try 3.5, which should not be enough to get to the next corner. So it's selected 4. So there's definitely not yet. So let's try 4. So it's 7 now. 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's at least one node there on the inside that's selected.
Okay, perfect. Yeah, thank you.
Yes. Okay, so I wouldn't be surprised. The reason he asked is probably this. If I'm not careful, I do this. I select nodes, it only picks the nodes on the face. So just to show that, if I plot it from there and I select nodes over there, 1, 2, 3, 4, 5, and that is 9 times 5, so it's 45. But we only have 33 selected. So if I just do the same, then now select the elements, and then say nodes by elements selected. So it's selected too far now. So let's clear that. Elements, all of these. It's not going to select all of them. Okay, so yeah, there it is, all 45 is now selected. Well, previously we only showed 33 selected, which was the surface element. Okay, so back to this. The next thing I want to talk about briefly is in some models we end up with a high stress somewhere, and I want to see where that is. So that's a really useful feature. So let's plot the stress in this case. Let's say I can't see where the maximum is. Argument's like, or I don't know where that's the only one. Now, one of the useful features is I can go to tools, I can specify a range. I want to see arguments like all elements with a stress above 100, so I can above 80. So anything from 80 up to any value that's just greater than the maximum. Select all elements in the range, and if I make visible, I can see where they are. Oh, that's interesting. So there's another high stress somewhere over there. Now this is where it's useful to grow the mesh. If I just picked, instead of 80, let's make it 99. Try slightly smaller, 95. So sometimes we end up with one or two elements only in that stress range. So then it's useful to grow the mesh to see where exactly that is. Now, another feature that's again vaguely related to this is, and by the way, I needed to use this recently, where we had a large model, 800,000 elements, kind of a shell model, and there was a couple of small spots with high stresses, and finding them and then expanding to see exactly where and why was really useful. Now, the other one I wanted to show is, let's say, and this is a common one, and we tend to forget this as engineers in some cases, is let's say, I'll average again just to make a prettier picture. So I want to add this into a report, but there's people that see red as failed. So let's say my yield stress was, argument's sake, 80 MPa, not 100. So I can make this from 0 to 80. And then everything in this unfortunate gray color is above 80, which is a bit of a pain. It doesn't look that good. And now this range from 72 to 80 suddenly looks like it's failing. So a trick to do that is to say 80 times 10 over 9. Okay, now 80 is the start of red. Now, where does that times 8 and 9 comes from? We've got 10 color ranges. So that scales it so that that point is a max instead of that a maximum. But we still have this weird gray color, which you're not certain is actually a good thing or a bad thing. So what we then can change, if we go to additional settings, I can say change color by legend pick. So I want to change that one to red. Now, the problem is I don't know what that red color is. I want the same. So I can say, let's just see what that is. 255 for red, 0 for everything else. Great. So go back, change that one, and make that 255, 0, 0. And then everything above 80, which is in this case failure, would then be colored in red, so then it's kind of obvious at least to show this. So let's take the other extreme case where instead of this, if this part was something like S355, I can change this to, I would say, 355 times 10 over 9. So this looks kind of boring. Everything is blue, but this simply says it's everything is low. So a useful plot to have, even if it doesn't in detail show what the actual stress is. It just makes it easier then to say, well, that is my allowed limit. Plot everything in the red above that, everything below that is a different color. Okay, so that brings me to the end of this section. I'm just checking if there's anything I've missed. Yeah, I don't see any additional things I wanted to cover. Okay, so thank you for joining. If there's any additional questions you have, something that wasn't clear, please let me know.
Thanks, Gerrit.
It was a pleasure.
Just showing you I wasn't sleeping. Not that I understood much of it, but I wasn't sleeping.
Yeah, yeah. Most of the session was on how Mentat functions. Some things we tend to not look at or forget. That actually makes
for me
life
it was
lots
important.
simpler.
No, for me it was important. Thank you. Have a good Friday further.
Good.
Thanks, Gerrit. Yeah, thanks, Gerrit. That was awesome.
Okay, pleasure.